The Constitution of India, Preamble. We, the people of India, having solemnly resolved to constitute India into a sovereign, socialist, secular, democratic republic and to secure to all its citizens justice, social, economic and political, liberty of thought, expression, belief, faith and worship, equality of status and of opportunity, and to promote among them all fraternity, assuring the dignity of the individual and the unity and integrity of the nation. In our Constituent Assembly, this 26th day of November 1949, do hereby adopt, enact and give to ourselves this Constitution.
Happy morning, students. I hope you all are doing good, safe in your house, taking care of your health, drinking warm water, eating vitamin C, especially vitamin C rich food to develop your immune system. And let us pray God, children, this COVID-19, let it come to a halt so that we can meet very soon. And do not think about what is not happening. Don't think over the negatives or what is happening around us. Instead, just focus on the positives and try to attract positives. So here I just want to share you a small story. There was an old saint. He used to sit under a tree, and people from that particular village, they used to go to him and they used to share their problems. Every time, most of the people, they rush to this saint and they gather around him and they keep on telling their problems to this saint. So this saint was just thinking, why always people speak about problems? Why they always cry over the problems? So what he decided is, he wanted to teach them a lesson. So as he planned, when all the people were gathered, so what he did is, he narrated a joke. He cracked a joke and everyone turned into laughter. Everybody were laughing so high that they were screaming, yelling, they couldn't control their laugh. After a couple of minutes, he cracked the same joke again. But then the number of people who were laughing were less. Not all the people were laughing, only very few people were laughing. After some time, he again cracked the same joke, but then what happened? There were nobody were laughing. Everybody kept quiet because they were telling how much time that we can laugh if you are cracking the same joke. So the saint replied, this is what is reality. If you cannot laugh for the same joke again and again, why you people keep on crying over the same problems again and again? Problems often come in our life. Life is something where we have ups and downs. Definitely, every downs will give us a strength to come up in our life. So children, I want to tell you at this point of time is, we know we are not facing each other. You are at home, we are in our school. Definitely you are not finding your friends to share your feelings, or you are not with your teachers to enjoy your school life. But this is not the end. Definitely all these downs are going to get stopped. We are going to have a time where soon we are going to meet each other. So don't ponder over these negatives. Instead, at this point of time, how I could manage my time effectively, how I could do my work productively, how far I can become myself more efficient. So these are the things that you should start thinking and make yourself independent and confident. So I want all my children to continue your work productively, be positive, keep yourself energetic, because there is a lot to go in our life. This is just a sample that God has given us. So every downs is going to give us a strength to come up in our life, and definitely we are all going to become great students, achieving more success in our life. Okay, so wishing you all good luck, and let us get into today's chapter. Today's topic is Bohr's model. Last class we were learning about Rutherford's atomic model, where there was a gold foil experiment. Alpha rays were coming from a source hitting the gold metal, and you saw some of the rays were deflected, some remain undeflected. And that is the reason that we came to know that there is one region which is positively centered, which is called as nucleus. And around the nucleus we have circular orbits in which electron starts revolving around. This is what we studied. We also learnt about atomic number, mass number, isotopes, isobars. We also saw about the drawbacks of Rutherford model. But why it lead to another model by the scientist Niels Bohr? You have been studying about Bohr's atomic structure from 9th standard, right? Now Bohr's model was focusing on two main things, the development. One is the dual character of electromagnetic radiation. Electromagnetic radiation, from the name it is very clear that both electric and magnetic strength is available for one type of radiation. We call it as electromagnetic radiation. Now dual character, when I say dual character, two kinds of character. First one is a wave nature, the other one is a particle nature. Wave nature, particle nature. So when I say wave nature, we know crest and trough, we have studied in physics. And particle nature, what all the properties a particle should have, those properties will be there for this radiation, which we will be seeing now. And what was the second development by Bohr was, these energy in the form of radiation were in the quantized form. What do you mean by quantized? Small packets. They were in the form of a small, I will say in a closed cluster. That we call it as quantized form, not separate, discrete. It was in the form of a quantized, that is in one cluster. That is what the development by Bohr. And then when he studied about wave and particle nature, he independently did experiments to find out the wave nature of the particle. So how did he find out wave nature of electromagnetic radiation? It was developed. Though it was started by Bohr's model, it was James Maxwell who went in deep to study about the wave nature of electromagnetic radiation. That was in 1870. What he did, he was very sure that there is some sort of interaction between the charged particles. What do you mean by charged particles, children? I say electron. Electron is negatively charged. Nucleus is neutral, but though it has protons which is positively charged, we always say it's a positive center, that is nucleus. So these charged particles, it can be nucleus and electron, or it can be electron and electron. So there is always an interaction. What do you mean by interaction? Some sort of communication is there. So that interaction is there between the charged particles and also behavior of electric and magnetic field. When I say electrons are negatively charged, and we studied in cathode rays and canal rays in presence of electric and magnetic field, how these rays behave. Do they travel in straight line or do they move away from the straight line? So this scientist James Maxwell was very keen in finding out the behavior of the electric and magnetic field. So when he did the experiment, what he came to know, he said, when a charged particle is accelerated, what do you mean by accelerated? In physics, you've studied acceleration, velocity. In the car, you know, you have clutch, brake and accelerator. Accelerator is nothing but to raise your speed. You are going in a particular speed. If you want to raise it, you do acceleration, right? You just accelerate it. Similarly, when the charged particles are moving in one particular speed, I am going to accelerate it, I am going to trigger it, I am going to make it move little bit faster. So when the charged particles are accelerated, electric and magnetic fields are produced and they are transmitted. Electric fields and magnetic field will be produced and they are transmitted, means from one place to another place alternately. Sometimes it will be produced, then it will be transmitted, produced, transmitted. So this takes place in an alternate way. But these were in the form of waves. Which were in the form of waves? This electric and magnetic field were moving in the form of waves. In physics you have studied, no, crest and trough, ups and downs. So this was like in the form of waves. So he gave a name which is called as electromagnetic radiation. Radiation is nothing but production and transmission. For the waves it was given as electromagnetic radiation, where both electric and magnetic field are produced, are radiated. It's in the alternate way. So now we will study about the extension of electromagnetic radiation. James Maxwell, when he was studying about the movement of the electric and magnetic field in the form of waves, he was finding something similar to that of light. When I say electromagnetic radiation, something that is related to light. So then he came into a conclusion that, as we already know, light is made up of lot of particles, corpuscles we say. In physics you would have studied, light is made about particles. But we know that light has got this thing, but we didn't study about the wave nature of light. That was found out only in the 19th century. In the 19th century, scientists took so many experiments to find out the wave nature of light. That is, the light could move in the form of radiations. So there were so many properties with this oscillating electric and magnetic field which were complex. Complex means very hard to study, very hard to understand. But then they came into a conclusion about few simple properties which we could easily understand. The first one was, these oscillating electric and magnetic field, they were perpendicular to each other. You know what is meant by perpendicular? When an electric field is moving like this and a magnetic field is moving like this, they form an angle that is 90 degree, which we call it as perpendicular, forming 90 degree right angle, right? So these electric and magnetic field, they were forming right angles to each other, and also both this electric and magnetic field, they were perpendicular to the direction of propagation of wave. Say if my wave is moving like this in a straight line, electric field and magnetic field, in a textbook page number 34, it is given to you, where electric and magnetic field are already perpendicular and the both are perpendicular to the direction of propagation of wave. What is propagation? Movement, the way they move. Right, that's the first property. The second one is, sound and water waves need a medium. Sound and water, definitely it needs a medium. Medium means it can be air, it can be water, right, rarer and denser medium. But these electromagnetic waves, unlike our sound waves and water waves, they don't need a medium, which means they can also travel in vacuum, right? So they don't require a medium. There were many types of electromagnetic radiation. When I say electromagnetic radiation, it's a huge types of electromagnetic radiations are there. How it was designed, how it was formulated, only with respect to the frequency and wavelength. What is frequency, children? Again, I am coming to physics, because when we say physics and chemistry, they are interrelated. In physics, you have studied about frequency, number of oscillations per second. So frequency means, in normal English term, in frequency means how frequent you go to school, how many times you visit this place, that is called as frequency. So frequency or wavelength, depending on these two factors, there are so many classifications of electromagnetic radiations. There were different units also to represent this electromagnetic radiations. And how are they characterized? When I say a particular electromagnetic radiation, they are characterized by two main parameters. One is a wavelength, the next one is a frequency. Remember, children, these two are the most important characteristic property of an electromagnetic wave. First one is wavelength, you write lambda, SI unit is meter, just like our length, wavelength of light, wavelength of visible light, wavelength of ultraviolet light. Frequency, frequency, you mention this symbol V in a written texted one, and the SI unit is Hertz. Okay. In vacuum, all the electromagnetic radiation, they travel at the same speed. That is, I told you electromagnetic radiation do not require a medium. So in vacuum, all the electromagnetic radiation, they tend to travel at the same speed. And what is that speed? It is 3 into 10 power 8 meter per second. We know meter per second is the SI unit of speed or velocity. So C is the symbol used to write the speed of light, and this formula C is equal to nu lambda. The speed of the light is equal to the product of frequency into wavelength. It's more important, children, because any two parameters will be given to us and we need to find the third one. So it's very important. There's one more quantity which is used in the spectroscopy is wave number. That is, you put V and you put a dash on the top, which we call it as wave number. So wave number is number of wavelength per unit length. Number of wavelength per unit length, and it's a reciprocal of wavelength, so its unit will be meter inverse or centimeter inverse. I hope you understood about the properties of electromagnetic radiation. Right, now we will do 2-3 problems. We'll do 2 problems and then we'll get into the particle nature. Okay, children. Now we'll get into the problems. The first question is, the Vivid Bharati station of All India Radio Delhi broadcast on a frequency of 1368 kilohertz. Calculate the wavelength of electromagnetic radiation emitted by transmitter. See, which part of the electromagnetic spectrum does it belong to? This I will be giving you the details of wavelength and frequency of the complete electromagnetic spectrum. What is electromagnetic spectrum, by the way? I told you electromagnetic radiations are of many types, right? They have a huge classification. If you see in your textbook page 35, you can see here different colors. It starts from gamma rays, X-rays, UV rays, IR, microwave, radio waves, long radio waves. In the middle, UV and IR, you can see in the center there is a small region which we call it as visible light. So here I will be giving you the wavelength and the frequency for different electromagnetic radiations. So now you need not worry about it. Here let us see what is given in the question. The frequency of the wave is given in kilohertz. So let us convert into hertz. So kilohertz is nothing but into 10 power 3, that is 1000. So 1368 into 10 power 3 hertz, the unit is nothing but seconds per second. So you put second inverse. And what is C? We already know C is the velocity of light, or I will say speed of the light. There is no change in that, it is a constant value, 3 into 10 power 8 meter per second. Now using the formula C is equal to nu lambda, let us calculate the wavelength. Wavelength equal to C by lambda. The value of C you put here and value of frequency. Then when you divide it, you get the value for the wavelength. Do not forget to mention the unit. Unit is very important because it carries quarter mark. So do not miss the unit and do not lose your marks, children, because it's very important whenever we do problems. Every single parameter, unless and until it is a constant, definitely make sure that you mention the unit. You don't forget it. So this is the first question. And if you see the next question, what is given in the question is, calculate the wave number and frequency of yellow radiation having wavelength 5800 Armstrong. See, 1 Armstrong is 10 power minus 10 meters or 10 power minus 8 centimeter. But here I want to convert into meter, so I put 10 power minus 10 meter. So wavelength is given. If wavelength is given, how do I find the wave number? We know reciprocal of wavelength is the wave number. So 1 by lambda. 1 by 5800 into 10 power minus 10, where I got the value for my wave number, and unit is meter inverse. And what is the next thing they have asked us to find is the frequency. Again use the formula C is equal to nu lambda, nu is equal to C by lambda. We know what is the value of C, 3 into 10 power 8 meter per second. What is the value of wavelength? Calculate the frequency. You are able to understand, children? Second one I am giving as a homework to you. Question is very simple. You have the two radiations, violet and red. Their wavelength is given. Nanometer, how you will convert into meter? 10 power minus 9 meters. So convert for each wavelength for 400 nanometer, that is 400 into 10 power minus 9 meter. Calculate the frequency. Nu is equal to C by lambda. We know the value of C. Calculate the frequency for violet. Calculate the frequency for red. So you get two frequency values and you write the answer in terms of frequency. You got it, children? So with this, the problems will be very simple in this chapter. Directly they will be giving you and you have to just rearrange the formula to do the calculations. Now we will get back into particle nature of light. We will see the particle nature of light. When I say particle nature of light, definitely it should show some properties. These comes under classical physics, which were not even be able to explain by the electromagnetic theory. When I say electromagnetic theory, it constitutes of both electric and magnetic field, but there were some failures again, and these were some of the important postulates or the points or the observations which has to be covered. So out of the four, today we will be seeing the first two, nature, that is particle nature of light. The first one is nature of emission of radiation from hot bodies. When I say hot body is nothing but any substance that is heated, definitely it gives out some form of energy. It will be evolved, that you know, that's a basic science behind every substance when it undergoes heating process. Ejection of electrons from metal surface. When any radiation comes and hits a metal surface, what happens to that metal? Does it eject electrons? Does it excite the electrons to come out of the metal? Which is called as a photoelectric effect. Photo means light, electric effect, which we will be discussing further now. Third and fourth point are the variation of heat capacity of the solids. Every solid will not have the same heat capacity. Some can get heated very fast, some can get heated very late. It needs a lot of time for that particular metal or the body to get heated up. And the last one is the line spectra of atom, special reference which we will be seeing about hydrogen. The last two topics we will be learning in the next class. Let us focus on the first two. Any solid that is heated will emit radiation over a wide range of wavelength. What does it mean? Take an example of iron. Iron, when it is going to be heated, you know, slowly it turns little bit yellowish, gold color, it becomes red, sometimes it becomes blue or even it turns white. Overall a period of time, as the temperature increases, when the solid is getting heated, when iron metal is getting heated again and again over a long period of time, the temperature is getting absorbed by the metal surface, which emits the radiation in all the way of wavelength. That is, it becomes red, it becomes blue, it becomes yellow, it becomes white. So many different types of wavelength over a particular period of time because of the heating process. As temperature increases, frequency of the emitted radiation, because this metal, when it is getting heated, it is emitting the radiation. So when it is emitting radiation, what is happening? Along when I say wavelength, definitely it also includes frequency, because I told you electromagnetic radiations are characterized by two important parameters. They are the wavelength and the frequency. So when I say a particular wavelength of light is being emitted, definitely it possesses a particular frequency also. So as the temperature increases, the frequency changes from lower frequency to higher frequency, which means when I am going to heat iron, it first emits a frequency, a radiation of lower frequency, then to the next to higher, at last the radiation will be of the highest frequency. So here first it turns red, which is the lower frequency, last it becomes blue, which is the highest frequency. So the color change is from red to blue, which is in the region of lower frequency to higher frequency range. So such an ideal body, such an ideal is perfect. We call she is an ideal person. Ideal means perfect. So an ideal body that emits and absorbs radiation of all the frequency, you call it as a black body. What do you call that ideal body as? Black body. An ideal body which is able to emit and absorb radiations of all the frequencies, you call it as a black body, and such an emitted or absorbed radiation, you call it as a black body radiation. So now we will be learning about black body radiation and how it changes with temperature. Now let us see what was he studied about the black body radiation. He was very sure that there could be some relation between the intensity and the wavelength. What was his conclusion was that at a given temperature, at one particular temperature, if you see, the intensity of the light actually it increases with a decrease in the wavelength, it reaches the maximum and again it decreases. Same thing happened at the new temperature. So as the temperature increases, what happens? You see there will be the wave that is increasing, reaching a maximum and again it comes down. But all these theory was not giving a satisfied way because they were so sure that they said the radiations were in a continuous way, but it was not in a continuous way. And that was given by Planck, another scientist who said that these emitted radiations were in the form of discrete quantity. When I say discrete quantity, in the form of packets. So that he call it as quantum, and quantum is nothing but the smallest quantity of energy which is emitted or absorbed in the form of electromagnetic radiation. So E is the energy and he gave a formula E is equal to h nu, where nu is the frequency of that particular wave light and h is the Planck's constant which has a value 6.626 into 10 power minus 34 joules. So it is very important, that is a constant again. For any problem the value of h will be given to us in the bracket. Now we are getting into the most important, the second point of the particle nature, which is photoelectric effect. You can see a vacuum chamber here and you can see a detector, and this is a metal plate, and as soon as the light is formed here, the light strikes on the metal plate, it has been connected to a battery and also an ammeter to record the value of the current. So as soon as the light hits the metal plate, you can see the electrons getting ejected. It comes out the moment the light strikes on the metal plate, and the ejection of electrons is confirmed using the detector. So what are the conclusions that we have drawn from photoelectric effect are? Electrons when ejected from the metal plate, as soon as the light falls on the surface, but there is no time gap between the light that is falling on the surface and the ejection of electrons, which means it is not taking much time to eject the electrons after the light hits on the metal. It will be the same time spontaneously happening. As soon as the light hits the metal, the electrons are ejected. So such a understanding is between the ejection of electrons and the light that is striking. The number of electrons will be proportional to the intensity of the light. More the intensity of the light, more will be the number of electrons ejected. Am I right, children? If you have more energy, you watch more videos, you will be more energetic to do any work. If you don't have energy, what happens? You will become tired. So what you should do? You should eat good food at good time intervals to keep yourself energetic. Okay. So here number of electrons ejected is proportional to the intensity of light. Next, most important, every metal will have a threshold frequency. What do you mean by threshold? Minimum frequency. Threshold energy means minimum. Say red light is having a minimum frequency. So when the light hits on that particular metal, a metal which is having a frequency, the light, if it is not hitting with the frequency more than the frequency of the metal, there will be no photoelectric effect happening. Are you able to follow me, children? I am the metal and the light is going to come and hit me. I have a particular frequency. The light which is going to come and hit should have a frequency more than my frequency. That we call it as a threshold frequency. If this light is not having a frequency more than the threshold, then no photoelectric effect is observed, which means the electrons will not get emitted. That is called as threshold frequency. The kinetic energy of the electrons increases with increase in frequency. More the frequency, more will be the kinetic energy of the electrons. But you know children, though it does not depend, the number of electrons depends on the intensity, the kinetic energy do not depends on the brightness of the light, only on the frequency of the light it depends on. So these are the assumptions of photoelectric effect. Now if you see, we have one more thing which is related to our threshold frequency, children. Greater will be the energy of the photon. What is photon? Again, light particles. Greater will be the energy of the photon, greater will be the excitation of electrons. So you have a formula here which is h nu is equal to h nu naught plus half mv square. It's given in page number 38. About the dual behavior of electromagnetic radiation, please mark it important, because that is called as a work function h nu naught. I'll be telling you about one problem based on this h nu naught, which is not there as of now, it is concerned. So with this, our topic for today is getting over. Tomorrow we will just get into atomic spectra and also about the line spectrum of hydrogen. I'll be posting the videos related to the topic for today for your better understanding. So make sure that you watch the video, and if you have any doubt, do not hesitate, kindly call me, children. Thank you.
In 1913, Niels Bohr, a Danish scientist, proposed a model of the atom which was based on the Rutherford theory. Rutherford's theory had shown the atom consisted of a positively charged nucleus with negatively charged electrons orbiting it. Let's look more closely at the postulates of Bohr's atomic theory. According to the Bohr model, the electrons of an atom will move in circular orbits around the nucleus, in much the way the planets orbit the Sun. The orbits are fixed and referred to as stationary, having electrons that orbit without radiating any energy. Bohr described these orbits of different energy as energy levels or shells. He also described an electron's energy as quantized, meaning the electrons can be either one energy level or another, but not in between. The energy level in which an electron normally orbits is said to be its ground state. An electron can move to a higher level through the absorption of energy. Electrons which have moved to a higher energy level will be less stable and in an excited state. An excited electron will release the energy it has absorbed as it returns to its original ground state. The energy released by electrons will be in the range of wavelengths of energy detectable by humans in visible light. Bohr postulated that when electrons are closer to the nucleus, they require less energy than those orbiting from farther away. As a means of differentiating between the energy levels, Bohr numbered them. Energy level 1 will be closest to the nucleus, and the larger the number of the energy level gets, the farther away the electron will be from the nucleus. Bohr also postulated that the number of electrons found in particular energy levels will differ. Energy level 1 can hold up to 2 electrons, while energy level 2 can hold as many as 8 electrons. Summary. According to the Bohr's theory, the electrons in an atom will move in stationary, circular orbits known as shells or energy levels. An electron can move to a higher energy level by absorbing energy. As an excited electron returns to its original ground state, it will release the energy it has absorbed. Energy level 1 will be closest to the nucleus, while energy level with higher numbers will be farther away from the nucleus.